In this video, I'll just take a look at some miscellaneous applications of logs and exponentials. One you might find interesting is that the Richter scale measurement is actually based on logarithms, where basically x naught, the way I understand it, is x naught is basically a predefined intensity of a particular earthquake, and so other earthquakes are based on some factor of that. So for instance, here, an earthquake that had an intensity of 199,526,000 times that particular x naught earthquake is what they defined as the San Francisco 1906 earthquake. So to find the Richter scale measurement of that, you can simply take 199,526,000 times x naught and substitute it in this formula for x, and then when you do that, you'll get x naught over x naught cancels. So basically all you're getting is the common log of 199,526,000, and when you plug that in a calculator, you get a Richter scale measurement of 8.3. So kind of what's interesting about that is if you have a Richter scale measurement of, let's say an earthquake has a Richter scale measurement of 7 and another earthquake has a Richter scale measurement of 8. Well, since they use logs to get this, it really means that the Richter scale measurement 8 is 10 times as intense as the 7. And then if you had one with a Richter scale measurement of 9, it would be 10 times as intense as the one that measures 8, but it would be 100 times as intense as the one that measures 7. So it's interesting. You got to go 10 times the intensity to get to 8 from 7, but you got to go 100 times the intensity to get to 9, and likewise you'd have to go 1,000 times the intensity to get to a Richter scale measurement of 10. So that's about all I know about earthquakes, so I'll stop there. Now, pH is another example. There's a formula based on the hydronium ion involved in pH. So basically, the relationship is that pH is equal to minus the common log of the amount of hydronium ion. So if you're given a particular pH, can you find the value of the hydronium ion? Well, let's see. So let's plug in a value of 5.4. Okay, now it doesn't usually work real well when you have a negative for a log. So what we're going to do here is we're going to remove this negative by multiplying both sides by -1. So if I multiply both sides by -1, that basically will move the negative over here with the 5.41 and eliminate the negative over here, because a -1 times negative is just positive. And now, remember, this is a base 10. So if I wanted to, I could actually write this in exponential form and say, well, 10 to the -5.41 would equal the hydronium ion. And so now, putting that in a calculator, I get that the hydronium ion is 0.000039. And I don't know what the units are, but whatever the units are, that they would go along with that. Now, this last example is a pretty cool example that I think is oftentimes, because it's a little bit more difficult, some people may ignore this example, but it's a pretty interesting example. It's Newton's law of cooling. Basically, if you have an object, let's say you have an object that you know the initial temperature and you know the temperature of the surroundings, well, Newton's law of cooling actually gives us the relationship between time and the temperature change. So in this formula, TE is the temperature of the environment. So it might be the temperature excuse me, of the room or something like that. And then T naught is the initial temperature of the object, and T is the temperature of the object at any time T, and then K is a constant, and then little t is the elapsed time. So let's take a look at a simple example using excuse me, using this. Let's suppose a canned soft drink takes 5 minutes to cool from 75 to 65 degrees after being placed in a refrigerator, and the refrigerator maintains a constant temperature of 35 degrees Fahrenheit. What will the temperature of the drink be after 30 minutes? And then when will its temperature be 38 degrees? Well, let's see what we can do here. Well, the initial temperature of the object is 75 degrees. And TE is the temperature of the room. In this case, the environment is 35 degrees. That's the fridge. And then, so what is TE minus T naught? So in other words, TE minus T naught, that's the temperature of the environment minus the temperature, let's see, of TE minus T naught would be 75. Actually, I've got that backwards, I think. Yeah, I've got this backwards up here. It should be T naught minus TE. So I've got this written wrong. That should be T naught minus TE. Okay, so T naught is 75 degrees. The temperature of the environment is 35 degrees. So 75 minus 35 degrees is 40. Now, the temperature that we want to achieve is 65 degrees. Or that it's going to achieve is 65 degrees. And so it's going to achieve that in 5 minutes. So given this information, can I find the actual constant for the formula? Well, then it's going to be the temperature that it's going to drop to is going to drop to 65 degrees, and the temperature of the environment is 35 degrees, and the difference in the initial temperature and the temperature of the environment is 40 degrees. And then we have e to the kt, but we know t is 5, so we can put 5 in for t and get 5 times k. Alright, now if I subtract 65 minus 35, I get 30. So I get 30 equals 40 e to the 5k. Then if I divide both sides by 40, 30 divided by 40 is 0.75. So I get 0.75 is equal to e to the 5k. And then I can take the natural log of both sides. So I get natural log of 0.75 is equal to the natural log of e to the 5k, which is just natural log of 0.75 equals 5k. And then to solve for k, I can divide by 5. Now, I went ahead and got a decimal out to 5 places here. So k was negative 0.05754. So therefore, I can plug in negative 0.05754. And when if I want to find the second question would be, when will the temperature, let's see, what's this first question? What will the temperature of the drink be after 30 minutes? So once I've got the model, I can now find the temperature of the drink after 30 minutes by plugging 30 in for the time. So there's my K. So here's how it works. If you go back and look at this formula, it's the temperature of the environment plus the difference in the initial temperature in the environment times e to the kt. Well, so the temperature of the environment is 35. We know the difference in the initial temperature in the environment is 40. And then e to the kt would be e to the negative 0.0574 for k. And then t is 30 minutes. So when I multiply this together, 40 times e to this power, I got 7.1. So I got that the temperature after 30 minutes would actually drop to 42.1 degrees. Now the next question I asked, I said, when will the temperature be 38 degrees? So what I want here is I want 38 degrees. And so I'm going to put 38 degrees in for the temperature, and I'm going to solve for T. There's a T right there. It's hard to see. So I'm going to have 38 equals 35 plus 40 e to the negative 0.0575 T. And then if I subtract 35 from both sides, I get 3. And then I can divide both sides by 40, and I get 3 over 40, which is 0.075. And then I can take the natural log of both sides, so I get the natural log of 0.075 is equal to the natural log of e to the negative 0.0575 for T. And then I can divide by the negative 0.05754 to get T. So I take natural log of 0.075 divided by negative 0.05754, and I get 45 minutes. So 45 minutes. So in 45 minutes, I would expect the drink to reach 38 degrees. So it's an interesting application there. I apologize for getting the formula backwards here, but I just got these two switched on you. Okay, well, I know you've seen on some of these crime shows them talk about the time of death, but let's take a look at how they can actually use this Newton's law to determine time of death. Suppose a body is found in a room that has a constant temperature of 72 degrees Fahrenheit, and the temperature of the body is taken and found to be 85 degrees Fahrenheit. 30 minutes later, the temperature of the body is taken again and found to be 81 degrees Fahrenheit. Let's estimate the time of death. Okay, well, let me show you how I'm going to do this. First of all, I'm going to use the correct formula this time, but the temperature of the environment is 72 degrees. And then if you take the initial temperature of the body, which was 85, and the temperature of the environment 72, and you subtract those, you get the initial temperature minus the temperature of the environment is 13. So I'm going to have 13 e to the kt. Now, let's use t equals 30 minutes. Well, when t is 30 minutes, that gives that the temperature of the body is 81 degrees. So let's put in 81 degrees for the temperature of the body, and then 30 minutes here for t. Alright, so if I subtract 72 from 81, I get 9 equals 13 e to the 30k. Then I can divide by 13, and I get 9/13 e to the 30k. And then if I take the natural log of both sides, I get natural log of 9/13 equals natural log of e to the 30k, which is just 30k. So the left-hand side's, I'm just going to put that over here. So that's going to be 30k equals this. And then to solve for k, I divide by 30. Well, that gave me the constant to be negative 0.01226. So now let's put k back into the function. So I have 72 plus 13 e to the negative 0.01226 t. The t is kind of hidden there. All right, now we know that normal body temperature is 98.6 degrees. So that's what we want to do. We want to find at what time the normal body temperature is 98.6 degrees. So we put 98.6 now, and we're going to solve for this t. So I'll just go through the arithmetic here. If you subtract 72, you get 26.6 equals to 13 times e to this power. And then if you divide both sides by 13, you get 2.0462 equals e to this power. And then if you take natural logs, you get natural log of 2.0462 equals natural log of this. And of course, the natural log of this is just the power. And then if you divide both sides by negative 0.01226, you get a negative number, which is actually negative 58.4 minutes. So the answer is negative because it was in the past. So about 58 minutes before the first measurement is the estimated time of death. Okay, so of course in practice they use a computer program to do these calculations, but anyway, it's kind of interesting to see how it's done.